Okay, let's dive into this. Welcome to This Explainer. Today, we're completely demystifying Bernoulli's theorem. We're taking the core concepts straight from play chemistry's breakdown and translating the physics of fluid flow into something that's, well, totally intuitive. Let's get right into the hidden physics of the world around us. Section 1. The pipeline and pressure, a real-world problem. Instead of starting with dry, boring math, let's imagine you've got a pipeline, and you need to get water flowing through it. Here's the central mystery. How much pressure is actually needed to make that happen? Think about it. Whether it's municipal plumbing right under our streets or massive industrial pipes, you need exact measurements to get fluid from point A to point B effectively. We literally can't just guess.
Moving on to Section 2, the main rule, Energy Balancing Act.
To solve our pipeline puzzle, we need a guiding rule, which is Bernoulli's theorem. So the crucial point is, at its absolute core, it states that when a fluid flows through a tube, the total energy at the starting point absolutely must be exactly equal to the total energy at the end point. Nature doesn't just lose or gain energy out of thin air, right? Whatever energy you start with at the entrance, you have got to have at the exit. It's a perfect balancing act.
This brings us to Section 3, Deconstructing Energy, the three components.
We know the total energy has to balance out, but what actually is total energy when we're talking about flowing water? Well, it breaks down into three physical parts. First up is pressure energy. That's the energy that comes directly from physically pushing the water forward. Next, we have kinetic energy, which inherently comes from the fluid's actual motion. And finally, potential energy, which is derived from height. And this brilliantly illustrates that if your pipe goes up a steep hill, the fluid gains energy simply from its elevation. It's like a giant puzzle coming together.
All right, Section 4, Building the Formula, Synthesis.
Let's move to and see how this builds if we treat it almost like a recipe. Step 1, we take our three energies, pressure, kinetic, and potential, and just add them all together. Step 2, to make this universally applicable for literally any amount of fluid, we divide all three of those components by the fluid's volume. That step is what gives us our standardized formula. And step 3, because we know the total energy at the start equals the total energy at the end, that whole formula has to equal a constant. And here is the final synthesis. P plus 1/2 rho v squared plus rho gh equals a constant. Now, it might look a bit complex, but you already know the anatomy of this equation. P is our pressure energy per volume. That 1/2 rho v squared, that's just our kinetic energy. And the rho gh is our potential energy from height. It's an incredibly powerful mathematical sentence that perfectly maps out our real-world logic.
Let's jump to Section 5, the real use, the payoff.
So, what does this all mean? Why does this even matter? Let's bring it back to our very first mystery. Now, what's really interesting about this is that by using this constant equation, if we know just a few basic facts about our system, we can calculate exactly how hard to push the water, meaning the required pressure, and the precise velocity at which it'll travel. Civil engineers and scientists use this exact fundamental logic every single day to design everything from the plumbing in your house to the complex aqueducts keeping modern cities alive. It's a real game changer.
So the next time you look at a pipeline, whether it's just the plumbing under your sink or a massive fire station hose, think about the invisible dance of pressure, motion, and height happening inside. They are all perfectly balancing each other out just to keep that fluid flowing. It really makes you see the everyday world differently, doesn't it? Thanks for exploring the hidden physics of reality with me.